Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composite MOOC course. Today is the third day of the ongoing week, which is the 10th week of this course. And yesterday we had introduced a new topic, and the topic was that what kind of relationship exists between the stress vector, which is sigma x, sigma y and tau xy, and the strain vector referred to with respect to extant directions, and what is the nature of the q bar matrix. So, this is the relation we want to develop, and we want to somehow relate this q bar matrix to the q matrix, because we can very easily calculate the q matrix q11 in terms of engineering constants. So, is there a way we can calculate q bar in terms of q, because if we can do that calculation, then I can also calculate this q bar matrix in terms of all the engineering constants. So, this is what we want to accomplish, and to start with, let us look at. So, we know that suppose this is my x direction, this is the y direction, and suppose the fibers are like this, then this is my L direction and this is the T direction, and the angle between L and x axis is theta degrees. Then based on principles of mechanics which you have studied in your previous classes, I can transform sigma x, sigma y, sigma z, sigma x, sigma y, sigma t or tau lt to sigma L in terms of tau L, tau t and tau lt using this relation. So, I can write that sigma L, sigma t and the shear stress is nothing but, so these relationships have been developed earlier in your earlier classes. So, we will not capture that again. So, this is equal to a 3 by 3 matrix multiplied by this stress vector sigma x, sigma y and tau xy, and the elements of this matrix are c square, s square, plus 2 s c, s square, c square minus 2 s c, then I have s c, s c and c square minus s square. And what is c square? So, c square means cosine square theta, s square means sine square theta, and same thing, s means sine theta and c means cosine theta. So, the point is, if I know sigma x, sigma y, tau xy, then I can calculate sigma L, sigma t and tau lt if theta is known. Okay, I can calculate these things. So, we will abbreviate this matrix and we will call it a matrix T1, just a symbol, so that we do not have to write these 3 by 3 relations again and again. So, in brief, I can write sigma when measured with respect to LT axis is equal to a transformation matrix T1 times the sigma matrix when measured in xy coordinate system. Okay. So, this is equation 1. Similarly, there is a transformation matrix for strains also. Okay. And we will, since we are, if we used tensor strains, then the transformation for from LT to XY is identical, but because in our regular practice we tend to use engendering strains, and in engendering strain gamma XY is twice of the tensor strain. So, because of that reason the transformation matrix for strain is slightly different. So, we will write that relation also. So, if I have strains epsilon L, epsilon T and gamma LT, then these strains can be expressed in terms of a transformation matrix times epsilon x, epsilon y and gamma xy. Okay. And what are the elements of this transformation matrix? C square, S square, SC minus SC, C square minus S square, C square, S square minus 2SC, 2SC. So, this is there, and this I call it as T2, T2. So, in brief I can write this as strain measured with respect to LT coordinate system equals a transformation matrix which is T2, excuse me, times strain vector measured with respect to XY coordinate system. So, this is one equation and this is other equation. Okay. Now, we are going to merge these equations. So, this is equation number 1 and this is equation number 2. Okay. So, from 1 we can say, if I multiply the first equation by inverse of T1 on both sides, then on the right hand side T inverse of T1 minus T1 inverse of T1 times T1, they just become an identity matrix. So, it goes away. So, what I can say is that from 1 sigma xy, that is stresses as measured with respect to x and y axis, are nothing but inverse of T1 times sigma LT. Okay. But we know that sigma LT is what? We have shown several times now that sigma LT is equal to this Q matrix times epsilon LT, right. So, we will do this substitution. So, we know that sigma, when we are measuring with respect to LT coordinate system, is what? The Q matrix times the epsilon matrix measured in LT system. So, we can say sigma as measured with respect to xy frame equals T1 inverse of T1 times Q times epsilon as measured in LT coordinate system. Okay. Now, what we do is we replace this epsilon LT with equation 2. So, here I am expressing epsilon LT in terms of epsilon xy. So, using 2 we get sigma xy equals T inverse 1 times Q T inverse T. So, epsilon LT is what? T2 times epsilon xy. Okay. So, this is there. So, this is equation 3. We finally note that this is a 2 by 2 matrix, oh I am sorry 3 by 3, this is the 3 by 3, this is the 3 by 3 and this is a 3 by 1. So, I can combine all these 3 by 3 matrices into one and I call this combo as Q bar. Okay. I know how to calculate T inverse of 1, I know how to calculate T2, I already know how to calculate Q from engineering constants. So, if the material properties are known and if the direction of x axis with respect to L axis is known, then I know all the elements of all these 3 matrices and I can calculate the Q bar matrix. So, I can say that sigma in the xy coordinate system is nothing but a Q bar matrix times strain as measured in xy system. Okay. And what is Q bar? To explicitly define Q bar matrix. So, Q bar and Q are not same. Q bar is for a generally orthotropic lamina, Q is for a especially orthotropic lamina, but both are in state of plane stress. So, Q bar is for a generally orthotropic thin lamina in the state of plane stress and this is equal to T inverse of T1 times Q times T. So, inverse of T1 times Q times T2. So, this is again a 3 by 3 matrix, but it is a little different in terms of when we compare it to Q matrix. So, this is a 3 by 3 matrix and if I want to express it in for using it all its elements, it is a fully populated matrix. So, the Q matrix, if you remember, is not fully populated. Why? Because these 2 elements are 0 and these 2 elements are 0. And what that means is that the extensional stresses and the shear strains are not coupled and similarly the shear stress is not coupled with extensional strains because these terms are 0. The Q matrix is not fully populated, but the Q bar matrix in general is fully populated and we will write down their numbers. So, it is Q11, Q12 and the last element is called Q16, it is just a convention. So, we do not have to worry too much about it. Last element is called Q16, second row Q12, Q22 and Q26 and Q16, Q26 and Q66 and this is a Q bar matrix. So, every element has a bar on it. So, this is very important, otherwise it will create confusion. So, it is a fully populated matrix Q11 bar, Q12 bar, Q16 bar, Q12 bar, Q22 bar, Q26 bar, Q16 bar, Q26 bar and Q66 bar. So, if we use this matrix to connect the stresses and strains, then we have this relation sigma x, sigma y, tau xy equals Q11 bar, Q12 bar, Q16 bar, Q26 bar, Q22 bar and Q26 bar. Oh, I am sorry. The first element is Q12 bar because it is a symmetric matrix and the last line is Q16 bar, Q26 bar and Q66 bar times the appropriate strains. So, appropriate strains are epsilon x, epsilon y, and the shear strain gamma xy. Okay. So, couple of observations. Unlike Q bar fully populated, unlike Q bar is fully populated. Okay. Q16 and Q26 are, I will not say always, can be non-zero, and because they are non-zero, and so we can make two observations. Thus, shear stress generates extensional strain and vice versa, and further extensional stress generates shear strain and vice versa. So, this is the situation for generally orthotropic system, but even here the number of independent engineering constants is still 4, because Q11 bar, Q12 bar, Q16 bar only depend on what? Some sines and cosines which are not related to engineering, but they only depend on 4 independent values of Q bar matrix. So, the Q bar matrix has 6 constants, but at a fundamental level they only depend on 4 independent engineering constants or stiffness elements. So, this is the overall theory. So, what we will do is, we will just for purposes of completeness, we will write down the exact relations between different values of Q bar and Qs. So, we will write those relations. Q11 bar equals Q11 times cosine 4 theta plus Q22 times sine 4 theta plus 2 Q12 plus 2 Q66 sine square theta cosine square theta. Okay. So, if you know Q11 and Q22 and Q66, you can calculate Q11 bar using this relation. Q22 bar is equal to Q11 sine 4 theta plus Q22 cosine 4 theta plus this term is the same. Then Q12 bar equals Q11 plus Q22 minus 4 Q66 sine square theta cosine square theta plus Q12 times cosine 4 theta plus sine 4 theta. Okay. Q66 bar equals, so these are complicated relations, but if you know the mathematics, then you can compute them, and you can even create a small code which will compute all the Qs for your composite. So, Q11 plus Q22 minus 2 Q12 minus 2 Q66 sine square theta cosine square theta plus Q66 sine 4 theta plus cosine 4 theta. Okay. Q16 bar equals Q11 minus Q12 minus 2Q66, and this is cosine cube theta times sin theta minus Q22 minus Q12 minus 2Q66 cosine theta times sin cube theta, and Q26 bar equals the same thing, but it is just the other way around. So, it is cosine theta times sin cube minus this entire things times cosine cube times sin theta. So, we will make some more observations based on these relations. What we see here is Q11 is an even function of theta. What is an even function? That if I make theta as negative theta, cosine of negative theta and cosine of theta is same. Sine of positive theta is equal to negative sine of theta, but this is sine to the power of 4 and sine to the power of 2. So, Q11, Q12, Q22 and Q66 are even functions of theta. That is, if I make theta from, let us say, 30 degrees to minus 30 degrees, the values of the first 4 q bars will not change. However, Q16 bar and Q26 bar, they are odd functions of theta. So, if I make theta from 30 degrees to negative 30 degrees, we should, otherwise our calculations will be wrong, see that the value of Q16 becomes negative of its original value. So, these are bars, yeah. So, these are odd functions and these are even functions, okay. These are even functions. So, this is the conclusion of our discussion for Q matrix. Similarly, we can also calculate elements of the S matrix, but at least for today's class this would suffice. We will continue this discussion tomorrow also, and till then you have a wonderful evening, and we will meet once again tomorrow. Thank you.